We will continue today the treatment of the Ising model, which will lead us to the final part of this class, of this semester, and those ideas of phase transitions from the microscopical point of view. We describe the properties of ferromagnets, paramagnets, the connection of the behavior to what we observed for the Bose-Einstein condensation. All of this was on Wednesday last week, Thursday, I'm sorry. And now we are dealing with the Ising model. Now, the idea of Ising model is that we have spins. I described it to you in the last lecture for simplicity that the spins are sitting on a one-dimensional lattice. But in general, I can have any kind of a lattice. Okay? And the type of the lattice is also completely arbitrary, meaning you define it. And from now on, I will look on this lattice and I will say that at each point of the lattice, I have a quantity, which is the spin. The spin either goes down or it goes up. Okay? And there are two terms in the total energy of the system. Okay? So first of all, we can have an external field, H, magnetic field. We're looking at the magnetic properties. And we know that the energy, due to the interaction between each spin and the external magnetic field, it is minus H mu, which is the Bohr magneton for our case, as J. What is J? So we took a specific point on the lattice, J. The location of this lattice is Rj, and there is a spin associated with this lattice, which is Sj. Okay. Now, of course, this is just the interaction of one specific spin with the external field. In general, we have to go and count over all the possible spins that we have inside our system. J goes from 1 to n. Now, here we are looking on the property that H is pointed in one direction and Sj's can be either +1 or -1. Okay. You will see that this idea can be extended. So for all J, Sj is either -1 or 1. Okay. In general, it is a scalar multiplication between H that will have some specific direction and Sj that also can have specific directions. Here we're dealing with quasi one-dimensional system that H is in one direction and the possible variations of Sj is also in the same direction. Great. So this is interaction with external field. We also describe the self-interaction. So if we take this spin Sj and we take some other spin, let's call it Si, that's located at position I and has a position of Ri, so we know that the interaction between the spin Si and Sj would go as Si multiplied by Sj, okay? And we should have some sort of a minus sign in front of them. Why minus? Because we want the particles being posed, that interaction will cause the different spins to be aligned. Okay? So we don't really care if they're going to be aligned in this direction or they're going to be aligned in that direction. We only say that the probable situation is when they're aligned. This is some sort of interaction. We can call it spin-spin interaction, dipole-dipole interactions, whatever you want. Okay? So we have Si, Sj. There is some coupling constant, which depends on the distance, usually, between the position of the spin Si and the position of the spin Sj. So here we have Rj minus Ri. And it's only, we assume that it's only depends on the position or the distance between them. Now, of course, we don't want to look only on one specific interaction between two specific spins. We go and we perform summation of all the spins that we have in our system. So this is I goes from 1 to n. This j goes from 1 to n. Okay? And because when we use this summation, we basically counted twice over all the possible spins that we have inside the system. So we'll add just 1/2 over here. Of course, the minus should also be in front of all of this sum. So this is the Ising model. This is the energy. Those terms. So this is interaction with the external field. This is interaction between the different particles. Problem is the interaction term. If you remember what I was trying to tell you over and over again, that the only tool that we have is when the energy is an additive function of all the different particles. Okay? Now, so this is easy because we'll look on this and say, oh, Sj is independent of Si. But this part, okay, it is depends on the multiplication of the different terms, and this is not an easy task to solve. Okay? So the problem, the real problem, is the interaction term. And we'll see that specifically anything that interesting that happens in the system is only due to the presence of the interaction. Okay? Now again, because I cannot write down the energy, or at least at this stage, I cannot write down the energy as just a sum of self-energies of different particles, such that the different particles won't affect each other. Okay? This is the problem, this multiplicative term that we inserted over here. Now, it's not a fictitious term, because we know from physics that the dipole-dipole interactions, spin-spin interactions, they have to be dependent on the multiplication of the different states. Okay, so it's not something that we just put by hand and that it's artificial, completely artificial, just for the sake of the argument. No, it's a real problem that's coming from the physical definition of the interactions between the different spins. Okay. So let's try and see what happens for this model. And the first part will assume that, let's forget about interaction. So the solution of a free Ising model. This means that J Ri minus Rj equals 0 for all I and for all j. Right? So this is the first part. Great. How we solve anything? And basically when I'm asking you to solve something, I'm looking on the average spin. So what is an average spin for my purposes? So the average spin is this total spin of the system. The total spin of the system. It is a summation. I goes from 1 to n, okay, of mu si, which is just mu a sum. I goes from 1 to n over si. The si's are those specific values, which can be either -1 or 1 for all the different locations on our lattice. Okay? And we always use the same trick that the average of a sum is a sum of the averages. So the average spin is mu, a summation I goes from 1 to n over si average. Okay? So the basic quantity that we are interested in is this SI average. And specifically, we're going to use this free Ising case, at least at the beginning. Great. How? Questions? Yes?
If it wasn't a one-dimensional model...
It's not a one-dimensional model. You see, it's any kind of dimensional.
The spin could have more than... to...
Then I will put a vector multiplication, a scalar multiplication between the spins and the external field, and also a scalar multiplication between the different spins.
But when you are summing spins like that, don't you need to use like Arabesh-Gordon or something like that?
It would just be, in this model,
okay.
it would just be the average vector. That's
okay.
So, right? Because eventually it's still an average of something. Now, in my model, I could have spins. So it's based on some quantum mechanics, this quantization, I'm sorry, of the values of the spin. But it's just the definitions of the model. The moment that I have defined the possible states, I'm using just mathematical summation without any spinors, etc., etc., etc. It's not a part of the problem yet. There are different descriptions which are not Ising model, like Heisenberg model, and etc., etc. When you deal with those guys as spinors, and then the average is a little bit different. Not in this class, right? Great. So what do we do? As usual in statistics, yes. Yes, yes. So why do I choose to use this? I'm saying let's solve the simple case without any interactions. Okay, and then let's see what happens when I introduce interactions. Okay. Okay, and it will also help us in the future. All right. So what is the way that we always do solve problems? Now here the energy is not constant, right? Because there are fluctuations of the values of the different spins. Therefore, there is fluctuations of the total energy that we have inside our system. The number of particles is kept constant. Okay, the number of particles is kept constant. So we're looking on a canonical ensemble, right? We can write down the partition function, which is just a summation over all the possible values of e to the minus beta en. Now En is this guy, and it will depend on the different values of the spin. Okay? For different realizations of all the different spins, we have different states. And I have to count over all the possible realizations of all the spins. Right? So it is just a sum over all particles e to the power minus beta multiplied by minus a sum I goes from 1 to n h, well, this is I, this is j over here, h mu s I. Okay, all realizations of the spins, spin values. Okay. So I have here the summation over all realizations of e to the power beta h mu, a sum I goes from 1 to n over si, which is a sum over all realizations of a multiplication, okay, of e to the power beta I goes from 1 to n, e to the power beta h mu si. Now look, because there are no interruptions and I'm just summing over all the possible values of all the different si's, so this guy, okay, equals to what? It equals to a factorizable multiplication, which means is S1 goes from minus 1 to 1, e to the power beta mu h S1 multiplied by a sum S2 goes from minus 1 to 1, e to the power beta mu h S2 multiplied by S3 goes from minus 1 to 1, e to the power beta mu hs3, etc., 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 up to Sn goes from -1 to 1 of e to the power beta mu hsn. So it's a factorizable representation. Exactly. So you've seen how I did it already again and again for fermions, for bosons, and before that. Yes, because they are all independent of each other and there is no multiplication thing. I cannot do this if I would have this multiplication. Okay, because there is also S1 multiplied by S2. Where I should put it? Over here, over there. I don't know where to put it. And it's going to mismatch all the different sums. But if I don't have this term, this is always possible. I've did it already several times during this class. Great. This factorization is what is all statistical mechanics of canonical and grand canonical representation built on. You know how to factorize. You can factorize. You have this interactions, it's gone. Great. So what we see is that z equals to z1 to the power n, where z1 it is e to the power beta mu h minus 1 plus e to the power beta mu h multiplied by 1. That's it. So I can write it down as 2 hyperbolic cosine of beta mu h, and that's it. So the partition function z is equals to I'm sorry, 2 hyperbolic cosine beta mu h to the power n. Now, if you remember, what I actually need to solve is this SI average. SI average. How do I do it? Remember, the moment that I manage to factorize over here, over there, I treat all the spins as independent particle, and I can treat each and single one of them as if it is presented by the canonical formalism. What this means that I don't need to go over all the different z's. I just need to go to z1. Okay. So what is SI average? It is plus 1 multiplied by F1 probability that, or S1, that spin 1 has value 1 plus minus 1 F minus 2, which is probability that spin 1 has value minus 1. So what is this S1? F1 equals to e to the power beta mu h multiplied by 1 divided by z1 plus, that's it, F2 equals, I'm sorry, F minus 1, minus 1, it's not minus 2, minus 1. F minus 1, it is the probability that, that the particle or the spin has the value minus 1, so it is e to the power beta mu h minus 1 divided by z1. Okay. So what would we have? S1 equals to, I'm sorry, S1 equals to e to the power beta mu h divided by 2 hyperbolic cosine, 2 hyperbolic cosine of beta mu h minus, because of the minus sign over here, e to the power minus beta mu h divided by 2 hyperbolic cosine beta mu h. So S1, and it doesn't matter if it's 1 or 2 or 3 or 4. So S1 equals to hyperbolic tangents of beta mu h. And the total spin is just n multiplied, as we've seen before, this guy.
סטאס, מה זה מיו?
Bohr magneton.
ולמה אנחנו מכניסים אותו בספין הממוצע?
Because for the property, so why we have mu over here, this is not an average spin. This is average plus 1 minus 1. Spin is mu multiplied by this guy. So what we had an expression that S average is n mu S1. Okay? So think about as units, right? Spin have some specific magnetic units, or the energy is multiplication of a self-magnetization multiplied by the external magnetic field. So it has to have some specific units. S1 is unitless number, plus 1, minus 1. Okay. Equals to n mu hyperbolic tangents of beta mu h. Okay. So let's see how it looks like. This is h. This is s. And the hyperbolic tangents looks like this. Nothing interesting, right? Doesn't matter what beta is. You see, what was the idea? The idea is that we'll get some sort of a self-magnetization out of nowhere. This is what Pierre Curie observed, okay, and got a Nobel Prize for that. So we don't see any transition from ferromagnetism to paramagnetism, from paramagnetism to ferromagnetism. You won't see any hysteresis loops, nothing. Okay? Now, we assumed, or we said, let's see what happens if we don't have interactions. Okay? And this is what we got. You have external field, you go up. You have negative external field, you go down, and you will always live on this line over here. Yes?
It's paramagnetic.
It is a paramagnetic behavior. Pure paramagnetic behavior. Okay? Paramagnetic behavior is the behavior that when you apply external field, you will have some magnetization. You do not apply any external field, the magnetization is going to be 0. Okay? Great. So we understand now that the problem, or the hope for getting something which is not a paramagnetic behavior, is in the interactions. Okay? We neglected those interactions, but actually the only hope that something actually does have this this property is the interaction. Now, it is hard to solve those interactions, and as I told you, the first solution was obtained after 10 years, or was incorrect. It can be solved, this Ising model, in 1D. In 2D, it took more than 20 years to find the solution. It was solved by Lars Onsager for a simple quadratic lattice without external field at all. And it will take me something like 3 weeks to show you how the solution goes. It's really long and hard. But long before Lars Onsager, and there was found a neat technique that explained why approximately we do expect a ferromagnetic behavior. And that's the approach that we will learn, and it's called mean field approximation. Now, what is this mean field approximation? If we look on our different spins, and we single out one of them. Okay. Let's look on this guy. Okay. So the idea is, well, you know, we're looking on one specific particle. We're looking on one specific particle. There are a bunch of other particles, spins, I'm sorry, I'm misplacing particles and spin over. There are a bunch of different particles, spins around it. Now they're all fluctuating. They're getting up, they're getting down due to the temperature. They're fluctuating due to the interactions. They're fluctuating. At an average, this guy fills an average external field that is applied by its peers. Okay? So on average, it is affected by, so you think about a guy, you look to the left, you look to the right, you look up, you look down, you look forward, you look backwards, and you have different particles, and on average, they're doing something. Okay? They're doing something. This something is some sort of external interaction. Okay? Now, this external interaction, if you have external interaction, you will probably get an average spin, like we're getting over here. Okay? So the idea is, let's assume that there is some sort of an average interaction, mean average interaction, which is a mean field that the different particles inside this material are feeling. Okay? This mean field, according to this picture, creates an average spin. What is this average spin? I don't know what is this average spin. Let's call it M. So due to effective interactions with neighbors, the average spin is M. What is this M? Well, I don't know. I am introducing a parameter that I will later somehow need to decide what exactly this parameter is. I'm saying, well, there are interactions. If there were no interactions, he couldn't care less about its peers. But there are interactions, so in looking to left, to right, to up, down, in some its environment, and so there should be some average spin. What is the spin? I don't know. We call it M. Okay. Now, let's see what happens if I have some specific M. So remember, the interaction term depends on the multiplication of two spins. So I have Si multiplied by Sj. This is what the interaction term was combined with. And this is what I told you is the problematic term because of these multiplications I cannot factorize. Right? Beforehand I can. Z1, Z2, Z3, Z4. Everything is factorizable. Everything is solvable. I'm introducing this guy. I cannot factor all the different exponentials because they depend on each other. So I have to treat this guy. So what I'm doing, I'm saying the following. I'm saying, well, let's represent this guy in the following fashion. So we say like this. Si, I can write it down as M minus Si. Okay? So I'm saying, well, what actually is Si? On average, it should be equal to M. And there are some additions. What are the additions? The fluctuations of my spin around its average value. The same thing I'm doing for Sj. It's M minus Sj. Okay, great. So let's plug it inside. So we'll have Si minus M. I'm sorry. It's M minus Si minus M minus Si multiplied by M minus Sj. Okay. Now let's multiply all the terms, and we do keep this M minus Si and M minus Sj. So I have this multiplied by that, so it is M squared. I have this guy multiplied by this guy. So it is minus m minus si. I have, so we multiply this by this and this by this. I also have minus m, so from here to here, multiplied by m minus sj. And finally, I have minus m minus si multiplied by minus m minus sj. So it is m minus si multiplied by m minus sj. Okay? Yes?
למה אנחנו מניחים שיש להם אותו ספין ממוצע?
Does it matter if I'm taking this guy or the other guy? It has the same surrounding. Right? It has the same environment.
אנחנו מניחים שלכל החלקיקים יש אותו ספין ממוצע בכל הלטיס?
So the assumption is that since any spin on the lattice has exactly the same environment, we assume that the lattice is very, very, very large. Okay? So you look on one spin, it has the same environment and the same interactions. You look on completely different spin, it has the same environment and the same interactions. So on average, they should have exactly the same spin. Yes. Okay? Now, there is of course this question, what happens on the boundary? Okay? Because on the boundary, this argument doesn't work anymore. Okay? But we assume that the boundary is much, much smaller than the bulk of the system, and we neglect this effect of the boundary. It won't work if I have just 2 spins. It won't work. Or 3. But if I have 10 to the power 22 spins, it will work. I don't care about the initial conditions. I set the system, I let it rest, and after a while, all the spin will have exactly the same interactions. The initial conditions are not important when I'm looking on the equilibrium behavior. Okay? I'm assuming that the system will reach an equilibrium. For equilibrium, I assume that it doesn't matter where I started. The equilibrium is what's important. Okay? Great. So, mean field approximation. Now, so we have this term, which is good. There also are some fluctuations, and we neglect this guy. Because we're saying, well, on average, it's almost always m. There are some small fluctuations. So this is the first order. This is the second order. Let's forget about the second order. Okay? Why? Why not? Right? So in physics, we are trying always to perform whatever we can, okay, and not everything. Now, look what we've got. So we've got that the term SI Sj equals to m squared minus m squared minus m squared. So it is in total minus m squared plus msi plus msj. Now, remember the following.
סטאס, במשחק שהזנחת את מחיתתו שם באדום, כששורה אחת מתחת זה בדיוק אותו דבר.
No, I have neglected this part, but those guys are different. You see, if I open this, I will have SI multiplied by SJ. I don't have SI multiplied by SJ over here.
כן, אבל חוץ מה-SI ו-SJ, כל שאר הביטוי אותו ביטוי.
Yeah, but this is the crucial thing, the multiplication. The multiplication of SI and SJ, this is the crucial thing.
אבל זה הביטוי הראשוני שאנחנו...
No. So, right. And I'm saying that in this mean field approximation, any multiplication of SI by SJ can be approximated by its... With the red guy, it's not an approximation. You agree with me? There is no approximation. The moment I deleted it, it's an approximation. Okay? So you're saying, Stai, why you can do this? So yes, there are conditions when I can do this, and it won't always work, and it won't provide me the exact correct result, but will give me an approximate solution. Otherwise, you'll have to spend here another month for me to show you how Onsager solved it. Okay? All right. You will understand this in a second why it's important. So the crucial thing, we don't have SI multiplied by SJ. So let's see what is the interaction term look like. We need to look on 1/2 beta, right? A summation of I, a summation of j ri minus rj, okay? Si, sj. This is the interaction term.
Why beta?
Because you don't like beta, let's forget about beta. I'll put it inside afterwards. Okay? So I'm already calculating whatever will stand in the partition function. Interaction term. Okay. Now, instead of Si multiplied by Sj, I have this expression. So it equals to 1/2 a sum over I, a sum over j, the coupling constant or coefficient Ri minus Rj multiplied by minus m squared plus msi plus msj. So we have 3 double sums over here. So we have a sum 1/2 a sum over I, a sum over j, j Ri minus Rj multiplied by minus m squared. We have 1/2 a sum over I, a sum over j, the coupling coefficient Ri minus Rj over msi, and we have a sum over I, a sum over j, j Ri minus Rj, and we have msj. Let's solve it term by term.
Shouldn't it be in a minus?
Where?
Everything?
Where?
Everything.
Everything. You want to be. Forget. We'll get this minus afterwards.
Okay.
You can remember that there should be some minus. The only thing that's important is how to represent all of this. Okay. So we're looking on this part. This is 1, this is 2, and this is 3. So 1/2 a summation of I, summation of j, j Ri minus Rj, and I can get this m squared minus m squared out of all the summation because it's a constant. So I have minus m squared. Now, this is nothing random already. This is a specific function that someone has to provide to you, specific coefficients. Depends on what is the problem in front of you. So this is a function that somebody provided. So I know that it is minus m squared divided by 2, a sum over I, and I call the summation over j, Ri minus Rj, I call all of this j tilde. Now, does it matter, or does this j tilde depends on I when I count it over oj? So think about what happens. I had a lattice, and it's again part of this mean field approximation. And on this lattice, I picked up, now I plot something small, but actually it's enormous lattice. And I have 10 to the power 22 different sides. And I pick one specific random side. And I compute the values. So this is Ri. Okay. And I need to go and compute the value of this guy when I'm summing over all the different distances from this point to any different distance on the lattice. Because my lattice is enormous and it's huge, and every spin or every point on the lattice sees exactly the same environment, this guy is independent of I. Okay? So I have here sum over I, j tilde, which is a constant. The moment it's a constant, the second summation is easy. So I have minus m squared divided by 2, j tilde multiplied by n. N is the total number of sides on my lattice. Great. So this first integral is simply minus m squared divided by 2 j tilde multiplied by n. We go, so this is 1. We're going to integrate to the summation, double summation 2. We have this guy. Okay, so it's 1/2. I'm taking m out of the double summation, so I have m. I have a sum over I. I'm taking this si out of this first sum, so I have si. A summation over j, okay, of j r I minus r j. This sum is whatever we had before. So it is simply m divided by 2, a sum over I, si, multiplied by j tilde. Well, I don't know what the different si's are. They can be 1, they can be 2, they are random variables. But this is just as one single sum. What happens next? So this is the second double summation. The third double summation is what? I have a double sum, 1/2. I'm taking m out, and I'm replacing the summation. So if beforehand I summed over j, then over I, now I will sum first over I and then over j. So I have a sum over j of what? Of sj, a summation of I, j, ri minus rj. Now, does it matter if I sum over I or over j?
No.
No, because it's ri minus rj, absolute value. Okay. So this guy is the same as this guy. So what we eventually have? We have that 1/2, a sum over I, a sum over j, j, ri minus rj, si, sj, equals to the first double summation minus m squared divided by 2 and j tilde. We have plus m divided by 2 j tilde sum over I si plus m divided by 2 j tilde sum over j sj. Now remember, it doesn't matter if it's I of j because I just have it's just a dummy variable. So in total I have minus m squared divided by 2 and j tilde plus m j tilde sum over I si. Because this guy identical to that guy. We're almost done. Let's see what is the total energy of the system now. The total energy of the system is minus mu h sum over I si. This is interaction of the spins with the external field. Plus, we have the interaction term. It's actually minus, right? So we have minus m squared divided by 2 and j tilde plus m j tilde, a summation of I si. What we got at the end, we have m squared divided by 2 and j tilde, this is this term, and we have minus mu h plus m j tilde sum over I si. What happened? Do you notice what happened?
There is no interaction.
Exactly. So if you forget about this term, which is just a constant, it is a constant. So it's a constant addition to energy. So we have a constant plus a representational free Ising model. Okay? A representational free Ising model. This means that I can solve it because I know how to solve free Ising model. So all of these interactions eventually got me into the position where I represent everything, all the system with interactions, by effective particles, okay? And the only thing that I have to modify is this external field. Instead of having mu h, I'm having m multiplied by j tilde. You can say, yes, Stas, you succeeded, but I have a problem. What is the problem?
You don't know what m is.
I have no idea what m is. I have absolutely no idea at this point of time what m is. So I succeeded in representing everything as if those are non-interacting particles by creating effective field, mean field, but I don't know what this mean field is. Okay? So we'll see tomorrow how exactly we find m, and does it lead to phase transition and ferromagnetic transition, etc. etc. תודה רבה ונתראה מחר.
סטאס, אפשר שאלה?
כן.
היה כמה תרגילים
אבל הוא יעשה
שגם לאינטגרל כזה,
מוקדם, אבל...
יש x בחזקת משהו, p,
כן.
עם z במינוס 1, e ב-x, מינוס 1.
כן.
באינטגרל בין 0 לאינסוף.
כן.
והתשובות הן כאילו משהו כמו f של z